Uh, I'm going to be teaching chapter 8 here, which is Introduction to Metabolism. All right. Now, um, in previous chapters I've talked about what metabolism is, how that the thyroid gland is the gland that is responsible for metabolic activity in our system, how they secrete the hormone that we call thyroid hormones, T3, T4, that are responsible for metabolism. So I'm going to be talking about metabolism, introduction to metabolism in details here. Now, when you look at, there are two laws that we talk about predominantly, the first law of thermodynamics and the second law of thermodynamics. The first law of thermodynamics states that energy can neither be created nor destroyed, but can be transformed from one form to another. So that means, in essence, what that means is that when energy, so in photosynthesis, for instance, now you have plants that are going to get sunlight energy, and they will take the sunlight energy and transform it into what we call chemical energy. What we call chemical energy is the glucose that you eat. So we talk about photosynthesis. So they take light from sunlight, photon energy, and convert that energy into chemical energy, which is what we call glucose that you are going to eat. Then you heat the glucose and then you transform it to another form of energy. All that is happening is what we call first law of thermodynamics, which is saying that energy is transformed from one form to another. All right. Now, from that first law of energy of thermodynamics, then another second law came into place. Now, the second law states that that in the course of transfer of energy from one form to another, there will be increase in entropy, which means a state of disorderliness. And in the course of that, heat will be lost to the environment. So think about it. When you buy gas into your car, for instance, what you have put in your car is a chemical energy, which is octane. Now you put octane into your car, which is chemical energy. In the course of conversion of octane into uh, mechanical energy, which your car moves with it. Now, in the course of that conversion of chemical energy to mechanical energy, obviously it is lost into the environment. Now, when it is lost into the environment, that heat, you can't account for it. That is the second law of thermodynamics. So there will be a state of disorderliness, which is what we call entropy, all right, which in quotes release heat to the environment. So in any case, in any time when energy is going to be converted from one form to another, heat will be lost to the environment. The production and loss of heat in the environment is what increase entropy, which is a state of disorderliness. And that is happening in any case. Now, so if I heat chemical energy now, I heat glucose. If I'm going to convert it to mechanical energy, either movement, sand, like I'm talking now, heat is going to be produced. I'm going to lose heat. I'm going to sweat. And in the course of that, that is what that process is what we call second law of thermodynamics, a state of disorderliness, if it's released. All right. Now, metabolism, what do we call metabolism? Is just the sum of chemical activities, the totality of chemical activities that happen within our system. So the simplest way you want to bring metabolism to yourself is to think about it. So some of us, for instance, now you have lactose intolerance. In lactose intolerance, it simply means that your body is not able to break down, your system is not able to break down lactose properly. And so what does lactose breaking down mean? You are breaking down, you eat food that is rich in lactose, which may be ice cream, it may be yogurt, maybe milk. You eat food rich in lactose, and your body needs to break down that lactose into glucose and galactose because your cell does not understand lactose. They can only understand glucose or galactose. You remember that from chapter 4 and 5. Now, when you eat lactose, what is metabolism is that your body should be able to metabolize it. All right. So, you use that word casually, you say, I'm not able to metabolize it. All right. Now, when your body break it down into what your cell can use, glucose and galactose, that is what we call metabolism. That kind of metabolism require breaking down into smaller molecule. That type, we call it catabolism. So the kind of metabolism that require breaking down is called catabolism, which is what you see here. So you see, it releases energy by breaking down complex molecules into simpler molecules. That's the same example that you see in cellular respiration, which we are going to do in the subsequent chapter, that involve breaking down glucose to release carbon dioxide and water, which will also give you energy. Now, anabolism is when you are building up large molecules from smaller components. All right, that will be anabolism. So when you have small molecules that you assembled and then give rise to larger molecule, that is anabolism. So cases of anabolism, if you think of photosynthesis, for instance, small molecules and small molecule, water and carbon dioxide is used to build up sugar molecule. That is going to be anabolism. All right. So anabolism simply means an adding together, and I joke with it, I call it adbolism. All right. So when I joke with anabolism, I'm going to put it on the, I'm going to write it here. So when I joke with anabolism, I call it adbolism. All right. In essence, I'm just saying adding together. Then when I want to joke with catabolism, I call it catabolism, meaning cutting, breaking down into smaller molecule. So I call it catabolism. All right. That is just to tell you that this is cutting it into smaller molecule, and this is building it into larger molecule. Let's go. Now, generally, again, catabolism are described as downhill reactions, whereas anabolism are described as uphill, because one is breaking down, one is building up. Living things use energy released from the downhill reaction of catabolic pathways to power the uphill reactions of anabolic pathway. All right. So in catabolism, energy is released. In anabolism, energy is required. So you need energy to build up. Catabolic reaction release energy as well. All right. So that means, think about it. Any reaction that is catabolism will give energy to the environment. Cellular reaction, cellular respiration will give you energy. Whereas any reaction that is anabolism will require energy from the environment to build up. So some cellular respiration, photosynthesis, for instance, require sunlight, energy from sunlight before it can proceed. That reaction is taking energy from the environment. Whereas cellular respiration will give energy into the environment. So I'm going to be talking about that in a few minutes. So bioenergetics is the study of how energy flows. So I'll be looking at how energy flow in the environment. So energy is what we call the capability or the capacity to cause a change. All right. So energy is required to do work, to work. So it moves matter against opposing forces. Energy exists in various forms. Living cell must transform energy from one form to another, which is what we are talking about. Now, energy, kinetic energy. As I'm seated like this now in physics, they say energy have not done any work, because work means that there is going to be motion. So when there's no distance covered, physics says I've not done no work. So if I sit here and teach for 5 hours, as long as I am seated, no movement has been incurred. As long as physics is required, I have not done any work. So in physics, kinetic energy is the energy that has to do with motion. Does that make sense? So when there is no motion, there's no energy. In physics, no energy has been incurred. So kinetic energy is the energy associated with motion. Moving objects perform work by imparting motion to other matter. So for example, water gushing through a dam turns turbines. So thermal energy, for instance, is a kinetic energy associated with random movement of atoms or move of molecules, which in quotes will generate heat. So thermal energy is transfer from one object to another is called heat. So as like I told you, like second law of thermodynamics the other time, as energy is transferred from one time to another, one form to another, that is what we call heat, thermal energy. So light is another type of energy that can be harnessed to do work, such as in photosynthesis, right? Now, potential energy. So potential energy, um, it's like we said that kinetic energy is the energy in motion, then potential energy is the energy at rest. Now think about it. Potential is something that you have potential to use, is potentially there, but it's not used yet. So it's at rest. So potential energy is energy that matter possesses because of its location or structure. For example, water behind a dam possesses energy because of its altitude above sea level. Molecules possess energy due to the arrangement of the electrons in bond between their atoms. So the energy is there, but it has not been expended. So that's why it's not the energy in motion. Then kinetic energy is a chemical energy rather, is a kind of potential energy that is available for release, but it has not been released yet. Once it's released, it becomes kinetic energy. Right? So energy in motion is kinetic energy. When some elements are in reactions, they are moving together during a state of entropy, that will be kinetic energy. But when they are just together, bound together, uh, that will be potential energy. So complex molecules such as glucose are high chemical energy because energy is released as they are broken down into simpler products. So at the time before they are broken down, we have potential energy. In the process of breaking down, they have kinetic energy. Now, like we said that energy can be transformed or converted from one form to another. First law of thermodynamics. All right. So when you look at chemical energy, for instance, from food is used to perform work. We use that to work. That will be a form of energy conversion. It can be changed. Chemical energy can be changed to mechanical energy. It can be changed to sound energy. Those are chemical. First law of thermodynamic in action. Now, the kinetic energy that you have in muscle can be transformed into potential energy as a diver climbs higher above the water. That will be a case of kinetic energy change to potential energy. Potential energy also can be converted to kinetic energy while the guy as the diver falls down the water, that motion. All right. Now, law of thermodynamics now is the study of energy transformation in a collection of matter. I've talked about that. So, as an isolated system, such as liquid in a thermal bottle, is unable to exchange energy or matter with its surrounding. All right. In an open system, energy and matter can be transferred between the system and the environment. Organisms are open systems, so we absorb energy from light or food and release heat or metabolic waste to the environment. And I'll be talking about that. So, first law of thermodynamics now. So, it says that energy is constant in the environment. And that's why we say it cannot be destroyed, it cannot be created. It is constant. It's anything you do with energy is just to transform it. So plants take sunlight energy, they transform it into chemical energy. We take chemical energy, we transform it to mechanical energy. It's just transformation. So the first law of thermodynamics is also called law of conservation because you are conserving the energy. Whereas the second law says that because at any time when energy is converted from one form to another, it is lost. And what the heat cause is a state of disorder, which is what we call entropy. So every energy transformation or transfer increase a state of disorder in the environment for the process to be completed. So entropy is a measure of molecular disorder. You see that as molecules are in disarray or randomized. All right, so living organism increases the disorder of their environment through their metabolic activities. All right, so now you have lactose now, and you need to break it down into glucose and galactose. They are not going to all stick together and then be broken down. No, for them to be broken down, they have to be a lot of motion, a lot of movement. It's the motion that leads to breaking down process. And that is what we call entropy. Now, so processes that increase entropy in the universe can occur spontaneously, spontaneously. When it occurs spontaneously, it means that it can be fast without any special energy input, and I'll be talking about that. Now, processes that decrease entropy are non-spontaneous. Those will require energy input. I'll talk about that later when I begin to talk about exergonic and endergonic reaction. All right, so cells create other structures from less organized starting environment and materials. For example, you have simple molecules, they're ordered together into amino acid, and when they are ordered together, we call it polypeptide, which is what gives rise to protein. And we have complex other structures are also produced from simple starting material. All right, let's go. Now, the increase in order within living system is balanced by the catabolic breakdown of organized form of matter, which is going to release molecule heat into the environment. At a larger scale, energy flow into the ecosystem as light and exit as heat. Does that make sense? So what it's saying in essence is that you are going to trap plants will trap sunlight. So energy is getting into the ecosystem as light. Then plants take the sunlight, use it to build glucose. Then you're going to take the glucose, use it to work in your body. In the process of breaking it down to do a particular job, it will be lost into the environment. So it exits as it. So the evolutionary complex organism from simple ancestors does not violate the second law. All right. We'll talk about that. Entropy disorder may decrease in a particular system, such as an organism, as long as the total entropy of the system and the surrounding increases. All right, I've talked about this. I'll be talking about, okay, cool. So everything I've said I'm talking about, I'll be talking about it now. Now, there is something that we call delta G. Delta means change, all right? That's what you see here. It means change. Now, so changing gives energy or changing free energy. Gives free energy, we call it delta G. It can be simplified or referred to as free energy. Now, free energy is a portion of the system's energy that is available to work when temperature and pressure are uniform throughout the system as in a living cell. So you'll be seeing me talking about delta G. Delta G, it means gives free energy. And G means keeps free energy, and delta G means change in energy in the environment. I will explain that, and it will make sense as we go. Now, so changes in free energy during a reaction is related to temperature and changes in enthalpy and entropy. So this is delta G, which means change in free energy. This is delta H, which means change in enthalpy. And then you have delta H, which means change in entropy. And then you have T, which is temperature. So in essence, it's saying change in delta G. Delta G means change in free energy. Now, delta H means the total energy that is available. You are going to get delta G by subtracting temperature multiplied by delta S, the entropy, from the total energy that is available. So let's go. Now, so the delta G for a process can be used to determine whether it is spontaneous or not. Now, when delta G is negative, it is spontaneous. So if you do this reaction calculation now, you plug in the values. When delta G is negative, it means the reaction will happen without problem. When delta G is positive, it means the reaction will not be spontaneous. Does that make sense? All right. So delta G is what determines it's like the energy required for every reaction, right? So if delta G is negative, it means the reaction is spontaneous. If delta G is positive, it means the reaction is non-spontaneous. So those are the things we want to check when we are looking at delta G now. So again, delta G is negative for all spontaneous reaction. Delta G is 0 or positive for all non-spontaneous reaction. So every spontaneous reaction will decrease the system free energy. That's why it will be negative. Spontaneous process can be harnessed by cell to perform work. So let's go. Now, so all we need to calculate is to check the difference. So delta G simply means difference. We are checking the difference in the free energy. So the difference between the final and the initial. All right. So if a reaction has negative delta G, that means the system actually lost free energy and it becomes more stable. Let's go. Now, free energy can be thought of as a measure of system stability. So unstable system, we have higher delta G, and then the stable one, we seem to have lower delta G. All right, so for example, if a diver on a platform is less stable than when floating in the water, all right? Now, a drop of concentrated dye is less stable than when it is dispersed randomly through a liquid. Now, a glucose molecule is going to be less stable than the simpler molecule into which it can be splitted into. So a simpler molecule, if you break down glucose now and you look at it as CO2 and H2O, that is going to be more stable than glucose molecule by itself, right? Let's go. Now, so look at this now. So more free energy higher, and then you see at this point, there's going to be more free energy. Now, it's higher delta G, it's higher G, right? Higher Gibbs free, and it means that at this point, it is less stable. All right. Now, the other point is, so it's greater work capacity, but what we know that is less stable, higher G, right? Now, what do you notice here? At this point now, it's lower delta G, it's lower G, and now it's going to be more stable in this state. So the same thing, large molecule, less stable. Smaller molecules, more stable. So glucose by itself is less stable. It's going to have high delta G. But carbon dioxide and water, they are going to be less stable. They are going to be more stable, lower delta G. So lower delta G, more stability. Higher delta G, less stability. So equilibrium is actually the point where the forward and backward reaction are equal, just like if you do look photosynthesis and cellular respiration, the reaction is the same if you do forward and backward reaction. All right. That is what we call stability, when both the forward and backward reverse reactions are the same. I'll still show that to you. So systems never spontaneously move away from equilibrium. A process is spontaneous and can perform work only when it is moving towards equilibrium. Let's go. The concept of free energy can be applied to the chemistry of life processes. Now, this is what we are actually talking about. So it's going to make sense here to you at this point. Now, there is a reaction that we call hexagonic reaction. Now, from the word hexagonic, think of the word exit. So I'm explaining the whole process of what I've been talking about now, and I'm bringing it to perspective. Now, the word hexagonic, think about the word exit. So think about exit. So exit, I want to think about it this way, as that energy is exiting the system. So meaning that energy leaves the system. All right. So energy is released in the system. So that means if you have a reaction, so you see an hexagonic reaction, energy outward, energy leaves the system. So proceed with a net release of free energy to the surrounding. So a reaction that releases energy into the system is an exergonic reaction. Now think about it. Will a catabolic reaction be exergonic reaction? Yes, because a catabolic reaction will release energy to the environment. So if it's releasing energy into the environment, that means at this point, we say the amount of energy, that means delta G is going to be less than 0 because the reaction release energy into the environment. So that means the reaction, the energy at the reactant is going to be quite more. Then it will release some energy into the environment. And then the reaction in the product is going to be big. It's going to be small. So you want to think about it as in terms of glucose. I told you that glucose molecule, if you look at it here, come back here, you see that glucose molecule, which is going to be big molecule, have higher delta G. So, and if you come here, you see there's higher delta G in the product side, in the reactant side. Then when the reactant release energy into the environment, the product side will have less delta G. So the delta G will be less than 0. So if you think about this, if what you have here in the reactant side now, if you have, let's say you have glucose molecule here, let's say right here is glucose, for instance, right? It's going to have higher delta G here, higher G rather. Then some energy will be lost in the case of here. So some energy will be lost here. So as some energy are lost, that means, let's say what you have here now is 50 kilojoule. It's 50 kilojoule. And you see here that 30 kilojoules are lost. If 30 are lost, that means what you are going to have left here is now going to be 20. So you have 20 here. That's when the system has been broken down. In this case now, you have thinking of having carbohydrate here. Let's say, carbon dioxide, for instance. So you say you have carbon dioxide here. So at this point, we now have small delta G. So this is more stable, this is less stable. This kind of reaction, when delta G is less than 0, we say this is a spontaneous reaction. So we say this is spontaneous. Does that make sense? So the reverse, when you come here now, this is going to be non-spontaneous reaction. And obviously, of course, this is like you have a reverse of this. You have carbon dioxide here. You have glucose here. So you're going to have less delta G here, more delta G here. So that means, in quote, let's say you have, let's assume that you have just the same opposite. You have 20 kilojoule of energy here. Then this environment added 30 to it. This is what is going to happen in anabolic reaction, like photosynthesis now, for instance. So this added 20 to it, then the energy here is now going to be 50 kilojoules. So you see, it has increased. The energy here has increased to about 50 kilojoule. So in this case now, more energy has been gathered into the product side from the environment. This kind of process that adds more energy, in this case, the delta G is going to be greater than 0. And when that delta G is greater than 0, we say the reaction is non-spontaneous. Does that make sense? That is an endergonic reaction. And that's going to be anabolic reaction. It's a non-spontaneous reaction. All right? Now, so in exergonic reaction, the products store less free energy, you see that, than the reactant. So here, there's going to be more energy than the reactant. The reactant have less energy. This is a spontaneous reaction. It means that the reaction is favorable or is favored by energy. It will happen rapidly, spontaneously. Now, the Amount of energy, the magnitude of delta G determines the maximum amount of work an hexagonic reaction can perform. So example, 1 mole of glucose broken down during cellular respiration will make 686 kilocalorie of energy to be available to work. The chemical product of respiration stores this less free energy per mole than reactants. Now, breaking down bonds during chemical reaction does not release energy. It actually requires energy. All right. So if the products are now are now lower than the reactant, potential energy is released when new bonds are formed after the original bond breaks. Now, the other portion of it, which is the opposite of it, is in endergonic reaction. In endergonic reaction, more energy is required. So that means the product is going to gather more energy, because for the reactions to happen, it has to gather energy in the environment. So the product will store more energy than the reactant. You see that? And then delta G is positive because more energy is in the product than the reactant. So this kind of reaction are non-spontaneous. We say that they are endergonic reaction. They are non-spontaneous reaction because they require more energy. Now, as you look at this, I want you to be thinking of the process now. So a cell does three main kind of work: chemical work, pushing the endergonic reaction, transport work, pumping substances across the membrane, then mechanical work such as movement, contraction. Now, energy coupling, I'll be talking about this when I'm making the part 2 of this chapter.